In this introduction lecture on acids and bases, I'm going to focus on the definitions of acids and bases and some of their properties. You might find it useful to have the worksheet on the definitions of acids and bases available to you as I go through this. So by the end of chapter 16, you should be able to identify and define the three models of acids and bases. You will be able to discuss the relative strengths of different acids, including the difference between a strong and a weak acid. You will be able to calculate pH, which is a relative measure of acidity, and you will be able to apply the equilibrium concepts from the last chapter to acid-base reactions. So here are some common acids, and these are the types of acids. This is not the overarching definitions of the acids that we're going to use, but this is a way to classify different acids. And the first one I want to talk about is a binary acid. Hydrochloric acid is a common one. This is the component of your stomach acid. It's also sold commercially as muriatic acid for things like cleaning metals. And we call this a binary acid because the H, the proton, is directly attached to a nonmetal atom. We also have oxyacids. Sulfuric and nitric acid are two examples. And they're called oxyacids because the acidic proton is directly attached to the oxygen atom. Finally, we have carboxylic acids. The carboxylic acid group is this carbon double bound to an oxygen with then single bound to an oxygen with the H. So this COOH is the classic carboxyl group. Here are some common carboxylic acids you may be familiar with: vinegar or acetic acid, citric acid, and malic acid. And they all have this COOH group attached. Now, acids have a somewhat tart flavor. The acetic acid, if you've ever had vinegar in like your salad dressing, you'll know that it has a slightly tart flavor. Citric acid and malic acid gives tart flavor to their fruits. And you can see from the structure, they all contain this COOH group. That's what this is right here. And so with citric acid, it could be written this way, but you could also write it like this, where you have this chain over here, and then you have that C double bounded to an oxygen, and then that OH. And malic acid also has a similar format. So anytime you see this COOH, you know that it's a carboxylic acid, and the acid end has this structure. Some common bases. These tend to have more bitter tastes and feel slippery on your skin. Sodium hydroxide, you're probably fairly familiar with that. It's basically drain cleaner. Potassium hydroxide. We use lye. If you've ever heard of lye soap, that is sodium and potassium hydroxides, basically. Sodium bicarbonate, baking sodas, antacids, a source of CO2 if you're carbonating your water. We use sodium carbonate. This is the primary component of water softener. And ammonia. So ammonia is an interesting base, and we'll talk a lot about that as we work with problems later. But it's extremely common in cleaning products and also in detergents and fertilizer, explosives, homemade bombs and stuff like that. So it's a pretty interesting compound. This is where you'll want to have that worksheet available to you, because I'm going to go through these three different definitions of acid-base behavior. And so that's what you'll want to be watching out for as we go through this. So we're going to start with the Arrhenius definition. And this equation, this chemical equation right here, shows how we define an Arrhenius acid. So we have HCl. This AQ, remember, signifies that it's dissolved in water. And when it goes into water, it dissolves, meaning it breaks apart and gets surrounded by water molecules. And so we have this H plus, the proton, and then we have the chloride anion. So in this case, the acid is producing H plus ions when dissolved in water. And so I just want to give you a little bit of background as to why I'm calling these protons. So a hydrogen atom is a proton in the nucleus and then an electron outside of the nucleus. Well, if it loses the electron to become a cation, then it's only a proton. So that's why I'm calling H plus protons and why I pretty much exclusively call them that. So in this Arrhenius definition, it produces protons, or it produces H plus ions when dissolved in water. Now, the other thing I want to note is that in water, there's no such thing as a free H plus. It's always stuck to a water molecule. So H3O plus is technically correct. However, I know that that can be kind of a pain to write out. I also know that this class is mostly taking place on a computer and it's cumbersome to do H3O plus. So if you want to just write H plus as your proton, as your acid, that's fine. However, you definitely need to know that in water there is no free H plus, that it's always stuck to another water molecule as H3O plus. So if an Arrhenius acid increases the H plus or H3O plus or proton concentration in water, what does an Arrhenius base do? Well, here we see sodium hydroxide dissolving in water. So we have a sodium ion and a hydroxide ion. So we would say that an Arrhenius definition produces hydroxide ions when dissolved in water. So you'll have the sodium ions surrounded by water molecules, and you'll have these hydroxide ions surrounded by water molecules. The hydroxide ion does not stick to water in the same way that the protons do. So you just would see, if you could shrink yourself down and see this, you would actually see an OH minus, the negatively charged hydroxide anion in the water. So let's write out the complete and net ionic equations for the following acid-base reaction. So this might be old information for you if it's been a while, so we'll talk through it pretty slowly. So when you have a complete ionic equation, what I like to do is think of these as breaking apart into two separate ions first, and then looking to see how they will recombine, okay? So we know that because it is an acid-base reaction, we know what's going to happen is they will form water and a salt, okay? So acid-base reactions, which are also called neutralization reactions, form the product liquid water and some salt. Sodium chloride happens to be the salt for the reaction between hydrochloric acid and sodium hydroxide, but it could be something else. If this was potassium hydroxide, our salt would be KCl, for example. So just remember that all neutralization reactions, the products are water and a salt. And then if this is a strong acid and a strong base, as these both are, and we'll talk about those in a little bit, but just point out that when it's a strong acid and a strong base, the only products are water and a salt. Okay, so let's think about this. So if we have HCl, we know it's going to break apart into H plus and chloride. And remember, this is really H3O plus, but I'm just going to leave it there for simplicity's sake, and just know that that is aqueous, right? So it's there. And then we have this sodium and hydroxide, and we're forming our H2O liquid and our sodium and our chloride. Okay, so all I did was break every ionic compound into its ion pieces. Okay, so I just took all of these and broke them apart when necessary. Liquid water is not an ionic compound, so it stays as its full molecule in our complete ionic equation. Now remember, to write a net ionic equation, what we do is we cancel out the stuff that is the same on both sides of the equation. So what do I mean by that? Well, we have chloride aqueous and sodium aqueous on the product side, and we also have chloride aqueous and sodium aqueous on the reactant side. So these ions, these are called spectator ions. They're not doing anything. They're just watching the chemistry happen. So the real chemistry that's happening in this reaction is an acid and a base forming water. So our net ionic equation doesn't contain any of the spectators that aren't participating in the chemistry. The net ionic equation is the chemistry only. And so we would write that as H plus OH minus going to liquid water. So this is going to be the net ionic equation for every reaction between a strong acid and a strong base. Okay, note that I said strong. So it's not every single acid-base reaction, but for strong acids reacting with strong bases, this is always the net ionic equation. All right, let's move on to the Bronsted-Lowry definition of an acid or a base. So here we're showing our HCl and our liquid water, right? So they're reacting. And so now we have this hydronium ion that I had talked about before and chloride. So what does our acid do? We call this a proton donor. So in other words, this proton on the acid was donated to the water molecule. So now on the other side of the equation, the water molecule has the proton. So the chloride donated it. So the HCl is the acid because it functioned as the proton donor. So now you might be thinking, I bet I know what the Bronsted-Lowry definition of a base is. So we have NH3, which is ammonia, liquid water, and now we have this NH4+. So you can see that the H left the water and stuck over here. So if the acid is the proton donor, then you must be thinking the base is the proton acceptor. So I just want to point out that sometimes it makes more sense to think about the base as a proton acceptor. Other times it might make more sense to think about the base as increasing the hydroxide concentration of water. Now, you could see how ammonia would count as for both definitions. It really doesn't matter. There's no correct answer. They're both correct. It just depends on what you want to focus on. So I'm going to give you some more vocabulary that becomes really important when we're talking about the Bronsted-Lowry definition of acids and bases. So when you have something like ammonia, you have the base, NH3, and then you add a proton to it because, and then now you have this NH4+. It was the acceptor, the base accepted the proton. And so now we have what's called the conjugate acid. And so this is a conjugate acid-base pair. So the only difference between the two compounds in a conjugate acid-base pair is a proton. Here we have water as our acid, and then losing a proton to make hydroxide. That would be the conjugate acid-base pair, okay? So in our equation up here, we have NH3 acting as a base, and we have water acting as an acid. Water was the proton donor. Ammonia was the proton acceptor. So ammonia is the base, and then its opposite, once it accepts the proton, it becomes a conjugate acid. Water here is our acid, our Bronsted-Lowry acid, and over here it is now the conjugate base. Okay, base, conjugate acid, acid, conjugate base. So let's practice with this. So we have two equations here, and we want to label the Bronsted-Lowry acid, base, conjugate base. So I urge you to pause and then try it yourself and then resume the video. So the first thing that you want to do when you're approaching a problem like this is remember which definition you're using. So the Bronsted-Lowry acid-base definition means that it is a proton donor or acceptor. So then what you want to do is look for pairs that differ only by protons to figure out what the pairs are. And we see we have H2SO4 and HSO4 minus. So these clearly go together. And then we see, did this donate or accept a proton? Well, it donated one because it has one less proton. So this must be acting as a Bronsted-Lowry acid. So this has to be the conjugate base, which means that this H2O has to be acting as a Bronsted-Lowry base because it's going to accept a proton, and this would be our conjugate acid. And we can see that we are correct. We have our acid conjugate base pair, and then our base conjugate acid. So then if we look down here, we can see that water, instead of accepting a proton on this side, has now donated it. So it must be the acid. And then this guy here, this HCO3, has to be the base. And we are correct. The acid has donated a proton and conjugate base. And this base has accepted the proton. It is the conjugate acid. So water is really interesting. We call it amphoteric. This is a really important word because it tells us that water has a very unique ability to act either as an acid or as a base. Water can donate an H+, or it can accept an H+. Okay, so water can be either. So there's no one instance where you can say that water has to be the base because it's water. You would have to look at the actual chemistry that it's participating in to decide if it either donated or accepted its proton before you can know if water was acting as the acid or base. So let's decide, how do we know if something is a conjugate acid-base pair? Well, remember how we talked about the only difference is the proton. So let's look at this one. We have a CH3,3N, and here we have a CH3,3NH+, okay? So in this case, this guy here accepted a proton, so it could be acting as a Bronsted-Lowry base, accepting a proton. And so, well then, this would make it the conjugate acid. And so could this donate the proton? Yes, it could. Here we see we have H2SO4 and H2SO3. The difference here is in the oxygens and not the H, so this is a good candidate. And here we have HNO2 and NO2. And so we see that this is only missing the H, okay? So it's very likely to be this guy right here, and we see that we are correct. These are actually two different acids. Okay. Finally, we are going to talk about the Lewis definition, and we won't use this one quite as much in this chapter, but it becomes very important when talking about redox reactions, and you'll use this in organic chemistry all the time. So a Lewis acid and a Lewis base have to do with electrons, not protons. So we are going to be talking about donating and accepting electron pairs, and then when a Lewis and acid base interact, they form what we call an adduct. So the acid is always the electron pair acceptor, while the base is the electron pair donor. Now this is a little confusing because it's not donating the proton or accepting the proton in the way that the acids and bases did from Bronsted-Lowry or the Arrhenius definition, because the electrons don't physically leave the atom or molecule and go to the other one. They're still there. There's just a bond formed. The adduct is formed. So you have to look at where the electrons started. So the electrons started on the nitrogen here. So this is the base and this is the acid, and they form an adduct together. Bronsted-Lowry model focuses on the proton. The Lewis model focuses on the electron pair. And this would be our adduct here if we were talking about Lewis acid base chemistry. And so I'm going to show you something here. This might look a little bit busy, but I'm going to walk you through this picture. So we have these electrons, and so you can use a curving arrow to keep track of where the electrons are going. So, because remember, bonds are formed between two atoms when they share electrons or exchange electrons. So by following where the electrons go can tell you something about the chemistry that's happening. And so you're going to do this constantly when you take organic chemistry. So get used to writing these kinds of things out if they are confusing to you now. So you have the electrons, and you always have the arrowhead going toward, like away from the electrons toward the more positively charged thing. And so we have the arrow going from the water, which in this case is acting as a Lewis base, going toward this carbon dioxide carbon, which is acting as a Lewis acid. And then we have the electrons leaving this bond here and going here, because carbon can only form 4 bonds. So now we have carbonic acid. Okay, this is really, really important in your blood buffering system, and we will talk about that in the next chapter. Okay, so now that we've gone through these 3 definitions of acid and base behavior, if you haven't already, go back through that worksheet, make sure that you have it straight in your head which ones are which. And remember, there's not one correct definition. Choose the definition that makes the most sense based on the chemistry that is occurring in the reaction of interest.